Before we talk about new materials, let's have a brief recall about what we have learned on Wednesday. On Wednesday, this is the let's summarize what we have learned about ionic bonding. So, important thing is how the ionic crystal form. This involves three stages. The first stage is electron transfer. You have to let's make an example like sodium chloride. So electron transfer involves that the sodium need to release one electrons and to let chlorine to receive one electron. So this involves electron transfer and it reach S2P6 Artex stability, right? And step 2 is that the two ions, one cation and one anion, need to be attracted to each other by Coulombic force. Okay, so Coulombic force attraction let the cation and anion get together. And after that, you have one molecule. And from one molecule to molecules, so you have many molecules. This is called molecular agglomerate. Okay, so this is the ionic crystal formation. And then we need to think of the energy. Apart from repulsion force and attractive force, how about energy and the interatomic separation with cation and anion? So the energy, they get together. So you have attraction energy and repulsion energy. And you can, this equation represent the attraction for energy and repulsion energy, right? N stands for net. Okay, and this is N is a Born constant. Born constant is between 6 to 12. R is distant between two atoms, and A and B are the constant. So the second topic we talk about ionic bonding is energetic of ionic crystal formation. So this involves geometry factor, which is very important. You want to learn in the topic of ionic bonding is that the important factor is we call Madelung constant. So this kind of formation of crystal or molecular agglomerate, it has a one Madelung constant. This has another Madelung constant. So the number of the Madelung constant is different. I mean the value of the constant is different. Madelung constant is different. So, and then this Madelung constant, if we put the Madelung constant in the form of energy, so the energy when R reach to R0, R0 means equilibrium spacing. We can use this equation to represent the energy of the ionic bonding. Okay, M is Madelung constant, N is an Avogadro number. So when you put this together, you will think that this is related to lattice crystal, lattice energy. Okay, and then the topic 4 we learn in ionic bonding is that Hertz-Bohr-Haber cycle. We use sodium chlorine as an example, become sodium chloride. As you know, this chemical reaction involve 5 steps. There are 3 steps absorb energy, and then there are 2 steps emit energy. So the net energy is negative. So that means that this reaction will be more stable if we have sodium present of the sodium chloride. Right. And then the topic 5 is the lattice energies of the ionic solid and ionic ready. So this is an equation we want to tell you, and they have attraction energy and repulsion energy. And finally, we talk about the properties of the ionic crystal. So ionic crystal is brittle, strong but brittle, right? And then the ionic crystal is is let's use ceramic as an example. Ceramic is electrical isolation. Okay, it's non-conductive, and a thermal isolation. Okay, it's not very good thermal conductor. Right, and it's transparent because of band gap. Okay, right. This is what we have learned about ionic bonding, and today we have a new topic, which is covalent bonding. Covalent bonding. Before we talk about covalent bonding, let's think of the limitation of ionic bonding. What's the limitation? If we use an example of hydrogen gas, nitrogen gas, oxygen gas, and you want to use ionic bonding to explain the formation of these molecules, it seems it's not easy. For example, the important concept for ionic bonding is the electron transfer. And electron transfer, after the electron transfer, both atom has to reach S2P6 Artex stability. So let's use hydrogen as an example. For example, hydrogen gain 1 electrons, become hydrogen anion. And hydrogen anion reach Artex stability because it's a helium electron configuration. So hydrogen act as an electron acceptor. That's correct, right? This is correct. So, however, if you want to form hydrogen gas, H2, then another hydrogen need to receive 1 electron. Another electron need to release 1 electron. That means it's electron donor. But once you release 1 electron, there's no electron in the hydrogen atom. And then it didn't reach S2P6 Artex stability. No, it cannot. This is there's no electron at all. So this is wrong. So the problem is that if you use ionic bonding theory to explain nitrogen gas, oxygen gas, chlorine gas, it doesn't make sense to you. So another scheming was proposed by G.N. Lewis. And then he think that, wow, rather you electron transfer from one atom to another, we can think of why don't they share the electron together. So he think that the positive shear filling by electron sharing, this is better than electron transferring. Okay, and and then he need to explain why he has this kind of thinking, right? You cannot just say it. If you just say it, you are not scientist or engineering. You have to prove it. Okay, everything you need to, once you say it, you need to prove it. Otherwise, it's like 名嘴, right? Okay. Okay, so to make a field shield, this is important. So let's think of what is a covalent bond. A covalent bond. So a covalent bond forms hydrogen gas where the 2 hydrogen atoms share the 2 electrons. We need to share 2 electrons. So for example, we have 2 hydrogen atoms, and then each hydrogen has only 1 electron, right? So once we put 2 hydrogen atoms together, it becomes hydrogen molecular. And then these 2 electrons share to these atoms. It makes sense, right? And then these 2, because this atom was shared, this electron was shared, so these 2 atoms got helium electron configuration, right? So helium and helium. There's no problem. Okay, so you can use this symbol dot to represent the molecular, or you can use a bar between 2 hydrogen atoms. Okay, then how about nitrogen bonding? Nitrogen molecules. Nitrogen molecular, one nitrogen atom is S2, 1s2, 2s2, and 2p3, right? So you have 5 covalent, you have 5 electrons in the outermost shell we call valence electrons. right? Valence electrons. So you can also write helium as 2s2, 2p3. Use this as an electron configuration to represent nitrogen, right? So we have 5 valence electrons. And then the nitrogen gas, nitrogen molecules represent like this. Okay, so this is an overlapped volume here, and each nitrogen donates 3 electrons. Okay, each nitrogen donates 3 electrons, and to make 6 in the center to let nitrogen atom to share to each other. So this is called shared electrons. And because this involves bonding, so that's why we call bonding domain. Bonding domain. So not sharing electrons, not bonding domain. So this become neon from helium electron configuration to become neon electron configuration. Okay, so why we call this covalent bond? Because bond formation involves cooperative use of the valence electrons. So we use co and valent to make it become covalent. Okay, this is how the covalent bond can explain the description of the covalent bonds. Okay, so once you know that Lewis tells us that electrons have to share to each other between atoms rather than transfer electrons to each other. So, and now you have to draw the molecules. Okay, for example, you have 3 atoms and you put 3 atoms together. What kind of structure is the what kind of structure looks like of these molecules? So Lewis has some rules. Okay, Lewis tells us that first you have to center the elements with lowest AVEE. I hope you still remember what is AVEE stand for, right? Anybody want to tell me what is AVEE stand for? 0.5 points. You are earlier than other classmates, right? So you are entitled to get the points. AVEE, yes? Thank you. That's very correct. Okay, average valence electron energy. So this is the form of energy. So the atom, the element which got the lowest energy, and you had to put it into the center. And this is how it looks like. So in a metal, that's what we learned in the previous Kahoot on Wednesday, right? So you have metal doesn't like electrons. So metal prefer to release electrons, right? So the AVE is relatively low. So which is less than 11 electron volt, right? Okay. And then for the non-metal, the AVE are high, and then it's more than 13 electron volt. Okay. So if you have a molecules and there are many elements, so you find one element which is the lowest AVE and you put it into the center. And after that, you count all valence electrons. How many valence electrons for A element? How many valence electrons in V element? How many valence electrons in C element? That's example. Okay, and then step 3 is to draw a single bond from each surrounding atoms to center atoms. Subtract 2 valence electrons for each bond. You know, one bond require 2 electrons. So you have to use this. You have subtract 2 valence electrons from each bond. That's correct, right? Okay, step 4 is distribute remaining electrons in pair until each atom has 8 electrons in total. Okay, place non-bonding pairs on preferential atoms, that means surrounding atoms, okay, starting with the highest AVE. Okay, these are the 4 steps to draw Lewis structure. Right. Okay, so let's make an example of the SCl2O2. We call sulfuric chloride. Sulfuric chloride. Right. So the step 1 tells us that put the element which has a lowest AVE in the center. So which one is this? So sulfur has the lowest AVE. Oxygen has the highest AVE. So you put sulfur in the middle, in the center. And then you put the chlorine and oxygen surrounding the sulfur. So you might say, well, Professor, can I put this chlorine in this place, replace these two, and then put oxygen in this position? Yes, you can. Because if you think of this three-dimensionally, it doesn't make difference, right? Okay, you can just swap as you like. Okay, so the first one is sulfur. Sulfur has 3s2, 3p4, and you have 6 electrons. And then oxygen, you have 2s2, 2p4. And then that means you have 6 valence electrons. But because you have 2 atoms, so you have to put 6 electrons times 2, become 12. There are 12 valence electrons. And chlorine, you have 5 valence electrons. And again, you have 2 atoms. So that will be 14 valence electrons. And you add this up, and that will be totally 32 valence electrons. Okay, step 2. And now you start to put a bar or 2 dots. Here you put a bar between atoms, right? And each bar requires 2 electrons. Okay, so this bar represents a bonding between 2 atoms. And these 4 bars tell you that it requires 8 electrons. So you subtract 8 electrons. And that means 4 pairs of the electrons, right? So, and then you got 24. These 24 are the valence electron which has no bonding. Okay, so 12 pairs. And then you started to do these pairs. For example, oxygen, you have 6 valence electron, right? And then oxygen, you have 6 valence electron, and chlorine, you have 7 valence electrons. Chlorine has 7 valence electrons. Okay, and then now you put sulfur in the middle, and then that's how you draw the structure. Okay, and this is, I'm sure you all know this when you're in high school. So this is called bonding domain. Bonding domain. There are 4 pairs which are the bonding domains. And non-bonding domains, these are the non-bonding domain. Okay, this is important to draw the molecular structure in the for you to consider some of the complicated structures. Okay. Right, and this is called dative bond. Dative bond means that this bonding is the electron from this bond in this bond is all from one atom. So one atom provides both of the electrons. We call a dative bond. Okay. Right. How about the methane? Methane is that you have carbon in the center. Of course, because of AVE, you put a carbon in the center, and you have 4 hydrogen surrounding this center carbon atom. And then let's draw a box notation here first. So carbon is 1s2, 2s2, 2p4. So carbon has 4 valence electrons, right? So you use the box notation. You can draw like this according to alpha principle. I hope you still remember. So this is although you have 4 valence electrons, and these 2 electrons occupy in 2s orbital, and there are 2 occupied in p orbital. So this is electron configuration to let you know this. However, when you want to share 4 electrons to the 4 hydrogen, and then the bonding of this carbon and hydrogen has to be equal. So now the problem is how can you put the 4 electrons to this carbon to let it become H2P6 hybridization, H2P6 configuration. So there are only 2 pairs to fill here, not 4 pairs. So that's why, Pauling think that, well, in this case, we need to share electrons, carbon need to share electrons to the hydrogen, but need to have a 4 equal energy of the electrons. So Pauling think that, well, to fill 4 electrons hydrogen, we suggest to mix 2s and 2p states together. That means this is what we call hybrids. This is what we call sp3 hybridization. So we can put these 4 electrons into this hybrid shell. So in order to maximum the number of the bond, because this require 4 bonds, right, for hydrogen, okay, and to form 4 identical states. So this is not identical state, 4 identical states, but this is 4 identical states. So to make 4 bonds with the hydrogen, it will become more stable. It makes sense, right? It makes sense. So equivalent energy level. Equivalent energy level means that this energy level and this energy level are different, right? This is lower, this is higher. But you had to make it equal. So as you can see, the energy level diagram looks like this. 2s is low, 2p is high, but now you need to make it differently, okay? So originally, this is called carbon sp3 hybridized orbitals, and you have 4 identical hydrogen atom, and you make it like this. So this is what we call sp3 hybridization. Hybridization means that, the shape of 2s looks like this. The shape of 2p looks like this, a dumbbell shape. But you have to do hybridization. So the shape of this s orbital and the p orbital has to be mixed. So this one mixed with this become this. And you put 4 together, it looks like this. So this is 4 tetrahedral hybrid orbitals. The 4 tetrahedral sp3 hybrid orbitals. It looks like this. Okay, so 2s2, 2p2 become sp3 hybrid orbitals. And here show you that the energy will be equal. These 4 orbitals, the energy will be equal. But according to the conservation of energy state, you have 2 energy states, and now you also have 2 energy states, and also the energy will be between 2p and 2s. The energy from low to high, and this is low, this is high, right? So this energy of these 2 sp3 hybrid orbitals were between 2s and 2p. Okay. So mention is CH4 is a kind of field, right? sp3 hybrids the equal bonds energy, and you have to make it become equal bond energy, and then you have to make it equally spectral distribution in the space, right? So this is equal spectral distribution in the space, okay? And this bond we call sigma bond, and this sigma bond, the energy is equal, length is equal. And carbon share 1 electrons to hydrogen. Hydrogen share 1 electron to carbon. And this carbon become S2P6 artec, stable artec, right? Hydrogen become helium, stable artec. And the shape of this is a tetrahedral structure. Okay, length is about 108 picometer. Well, you don't need to remember this number. It is not important. Okay. So if you use a stick model to represent meson, it looks like this. If you use sphere model to represent meson, it looks like this. It's just the different representation of represent the meson. Okay, let's have a quick description of the covalent bonding. The covalent bonding is we use the meson as an example. We share electrons from carbon. Okay, there's a share electrons from hydrogen. Okay, so carbon has 4 valence electrons. Hydrogen atoms has a 1 single valence electron. And then covalent bonding stable structural configurations are assumed by the sharing of the electrons between adjacent atoms. Some people read adjacent. Okay, that's the same. It means the same thing. Okay, adjacent. Okay, so once we know the structures, and now let's think of the energy. The energy of the covalent bonding. So let's say that this is hydrofluoride. Hydrofluoride, as you know, hydrofluoride has is a single bond, right? So hydrogen donate 1 electrons, fluorine donate 1 electron, so they have a single bond. And then these both reach S2P6 or helium electron configuration, right? Okay. And this helium, this is neon. So when we think of the energy, let's think of the energy, bonding energy of hydrogen. The bonding energy of hydrogen is only 1 single bond. The energy is about 435 kilojoule per mole. How about the fluorine? Fluorine gas. Fluorine gas, the energy is about, the bonding of the fluorine gas is about 160. So when you take 1 hydrogen out, you take 1 fluorine atom out, you make it become hydrofluoride. And have a guess. What's the energy? For your common sense, you think, wow, this must be between 400 to 100, right? Between these two numbers. For us, if we think of this straightforward, it must be between these. But when we measure the bonding energy of this hydrofluoride, this number is, the bonding energy is much higher than hydrogen. The number is not between 435 to 160. And the scientists started to think, why? Why the energy is not between these two numbers? So electrons in hydrofluoride are not sharing equally. So they think, wow, these 2 electrons share equally. These 2 electrons share equally, but these 2 electrons doesn't share equally to hydrogen and fluorine. No, it doesn't. And why? And it's not if it's not sharing equally, then what happened? Were these 2 electrons close to fluorine, or were these 2 electrons close to hydrogen? Which one? So they think that, wow, these electrons might share to each other, but they shift to the place where they like. For example, in this case, these 2 electrons shift close to the fluorine gas, fluorine atom. So it's not equally sharing. And the reason we think is because of the electron negativity. We call it chi. I hope you remember this number. You remember this term, electron negativity. You know, when we study the traits of the periodic table. There are 4 traits, right? Anybody still remember? Atom, right? The atomic radius and the electron negativity and electron affinity. And one is what? Last one. First one, let me, I forget the first one. Atomic radius, right? First one, atomic radius. Second one is the chi, the electron negativity. The third one, the atomic affinity. Okay, the first one, you gain 1 electron, right? And you lose 1 electron. That's what? Ionization energy, right? Am I right? Okay. Right. So let's recall what we have learned about electron negativity. So electron negativity here we call chi. So ability of the atoms to attract electrons in a bond. Okay. So electron negativity means how much you like. Again, how much you like electrons. If you like electron very much, the number of the electron negativity will be high. So chi is a proportion of the AVE. So in this case, you know that, well, the chi, the number of the value of the electron negativity will be high for non-metal, will be low for the metal. Okay? Remember? Okay, non-metal, high chi, and low metal has low chi. Of course, except hydrogen, because hydrogen only have 1 electron. And this is the chi electron negativity values for all elements. As you know, the chi will decrease from this color from the top to the bottom. I hope you still remember. Oh, hydrogen is not in this location. Hydrogen is here, somewhere here. So it will decrease from the top to the bottom. Will decrease from the right to the left. And the highest is for ring, right? The chi is 4. Lower is Francis, okay, is 0.7. Okay. So this is the traits of the electron negativity versus the atomic number. Okay, so when we say about the covalent bond is not electron sharing, but it's not electron transferring, but also electron sharing. So we put these two together, and we have a number come out, which is we call ionic characters. So what is ionic characters? For example, ionic characters tell you that what is the degree of the ionic bonding. If the value is high, that means you have a high ionic character. For example, sodium chloride has a high ionic character compared to the chlorine gas. Why? Because chlorine gas, they share electrons only. But sodium chloride is ionic bond. So ionic bond is share electron but also shift electron. So this is the number I want you to remember, ladies and gentlemen. Ionic character is this equation. Please remember this and be honest. This is not difficult at all. So 1 minus exponential power minus this quarter, right? 0.25 is a quarter. The square brackets x chi a minus chi b and power 2. So it doesn't matter if you have a power 2, it doesn't matter you put a chi b in the front or chi a in the front, right? So chi a and chi b are the electron negativity for the respective element. So this is electron negativity here. So let me make an example for you. Magnesium oxide. Magnesium oxide if we take a look of the electron negativity number, magnesium is here is 1.2, and oxygen is 3.5. So let's use this equation and put this number into this chi A and chi B here, and you will get an answer. So please bring your calculator when you do your midterm exam. Okay, remember, bring your calculator. So ionic character is this. Ionic character of the magnesium oxide is about 70%. So that means there's about 30% not ionic. This is kind of the degree of ionic character, the degree of the ionic bonding. Okay, how about chlorine gas? If you put a chlorine gas into this number, what happens? It's 0, right? It's 0. So that means what? That means there's no, this is a pure covalent bond. It's not, this is about 70% ionic bond, something like this. What I want you to remember is this equation and also a calculator. So now let's go back to energy of the covalent bonding for the hydrofluoride. So how can we get this number? This number tells us that, well, Pauling saying that the calculation of the heteronuclear bond energy, heteronuclear means that you have two different atoms, two different type of element. Okay? And then, for example, is fluoride. So you use this equation. And ladies and gentlemen, I don't want you to remember this equation because this is a relatively rough calculation. So you have a square root of the covalent bond, pure covalent bond. Put these two numbers in here, and this is, and then plus 96.3 and chi H minus chi F power 2. Okay, this term is represent the electron sharing energy. And this term, so pure covalent. And this term is electron shifting, represent the energy of the electron shifting. And you might ask me, Professor, why is 96.3? Well, I didn't check the reason, but it seems to me this is a empirical equation. Empirical equation means that the number is, when you do many experiments and you find out this is the number to fit this equation. Okay, so this is partially ionic character. And this. So if you put this number in here and you put a chi into here, and the answer you can get is about 608 kilojoule per mole. And this number doesn't equal to this number. This number is the number which we measure the bonding. But this number is the number we get from the calculation. So it is not so correct, right? But the important message you want to get from this equation is that the energy is divided into two parts. First part is called electron sharing. The second part is called electron shifting. Okay, this is an important concept you want to remember. Okay, so between these two, so this number is electron sharing, right? The answer we get is 264. So as you can see, this number is between hydrogen gas and fluorine gas. Okay, so are you with me so far? This is not difficult at all, right? Okay. So if you don't understand, please come to me. I will personally explain to you in Mandarin. Okay. So before we introduce next topic, right, and now I want, because we know the ionic character, so we want to see that what is polar covalency. What does that mean, polar covalency? So Louis Pauling, he got Nobel Prize because he proposed this kind of polar covalency, this kind of things we need to know. So let's make an example of the chlorine gas, hydrochloride, and sodium chloride. So chlorine gas is a kind of pure covalent bond because electron 100% share to each other because you have two identical chlorine gas between each other. So this bonding, electrons share equally between two atoms. So there is no charge on atoms. It makes sense. Okay, so this is called non-polar covalent bonds. Then why Pauling got Nobel Prize is this. It's hydrogen and chlorine, of course, they also share a pair of electrons. But this pair of electrons likes chlorine more than hydrogen. So these two electrons is a little bit closer to the chlorine gas. And that's why we have some kind of polar appear in this molecule, which is because the electrons closer to chlorine. So you got negative here. You got positive here in this edge. You got negative here in this edge. But as a whole, this is charge neutral. There's no charge here. This is a neutral molecule. But inside you have electrons, which is more positively. You have place where it's more charged negatively. So this is what we call delta. The delta is partial negative or positive charge. So the bonding electrons share unequally between two atoms. So partially charged on atoms. And this is what we call dipole. Dipole. Dipole is neutral. Oh, if we take a look of this molecule, it's purely neutral, but a symmetry of charge. Symmetry of charge means that, you know, if it's negative here, it should be positive here. If negative here, it should be positive here. Symmetric. Symmetry of charge. So this is called dipole. And this bond we call polar covalent bond. Ladies and gentlemen, you need to know the definition of dipole and what is polar covalent bond. This is called polar covalent bond. Okay? And how about this? Sodium chloride. This is what? This is ionic bond, right? This complete transfer of one or more valence electrons to field charges on resulting ions. So this is what? Ionic bond. Okay? So the interesting thing for the polar molecules is that we think of this, if this is neutrally, if we take a look of this, excuse me. What are you going to say to me? No? Thank you. Thank you. Okay. Where are we? Okay. If you have a molecule which is neutral, but you have polar bonds, sometimes this polar bond will form a molecule called polar molecule, but sometimes not. It depends. Okay, so when we take a look at polar molecules, this is without electrical field between these molecules. This will be random distributed. Okay, although this is neutral, but you have a delta positive and delta negative here. And when you have when you put the electrical field between these molecules, this molecule will be aligned according to the side of the positive and the negative side. So this will be aligned. It's interesting. We are going to show you an example very soon, but not today. Okay, so you have polar molecular, and of course you have non-polar molecular. So this is non-polar molecular, right? Methane is a non-polar molecular, but you have polar bond because carbon and hydrogen is not, the electron doesn't share equally, but electron share but shifting to the carbon because of electronegativity, right? So this chi tell you that you have dipole, you have delta, you have dipole here. This is we call polar bond. And then if you put 4 polar bonds together to make it big, to form a methane, this is a non-polar molecular. No net charge displacement because all polar bonds equally omitted. Okay, so methane molecules is a non-polar molecular. Okay, so compared to hydrofluoride or hydrochloride, the molecular has a dipole. It has a polar bond, and also is a polar molecular. But methane, the case of methane is methane has a polar bond, has a dipole, but it's not a polar molecular. We call non-polar molecular. So non-polar moleculars is that non-polar moleculars results from either homonuclear molecules. Homonuclear molecules means that 2 atoms or 3 atoms or 8 atoms the same. For example, hydrogen P4, phosphor 4, and sulfur 8. If phosphor 4 and sulfur 8, they are all have dipole, have polar bond, but is a non-polar molecule. And also spectrally disposition of the identical polar bonds. Example is carbon. Example is methane. So how can you distinguish the polar or non-polar molecules? If you have a polar molecular, if you have polar bonds, you need to tell whether this is polar molecular or non-polar molecular, right? So in your midterm exam, I will give you a list of 10 molecules, for example. Okay, in your midterm exam, I will give you a list of 10 molecules and ask you to tell me, list the polar bonds molecule. List the molecule which has a polar bond, and also list the molecule are non-polar molecular and polar. Understand? No problem, right? If I give you 10 molecules, it's not difficult for you to identify the molecules which has polar bonds or which are non-polar molecules. Okay, so covalent bonding is normally is non-metallic atomic elements like this. And molecules contain dissimilar atoms. An element located on a right-hand side of the periodic table. So when you have periodic table, these elements, most of them are located on the right-hand side of the periodic table. And polymeric molecules are belong to covalent bond thing. So number of the covalent bonds, for example, carbon has 4 and chlorine has 1. Okay, Okay, next is ionic and covalent bonding. Let's mix these two together and let's discuss about this ionic and covalent bonding. So very a few compounds inhibit pure ionic or inhibit covalent bondings. Okay, because we learn this is called ionic character. And degree of either bonds types depends on what? Depends on the relative positions of the constituent atoms in the periodic table. And because they have differences in their electronegativity. Because electronegativity tell them that you can identify what's the ionic character of this molecule. So wider separation of this in the periodical table, the more ionic the bonding. So as we mentioned this before, you have one element here and one element in the left hand side in the periodical table, and one element in the left hand side in the periodical table. If you put these two elements together, it's very likely this molecule has a higher ionic character, right? And also, the closer atoms are together, the greater the degree of the covalency. If you put the element this one and this one together, it's very likely to have a covalent bonding. Okay, so Lewis and Pauling. Lewis is another great person, but it's like a Sommerfeld. Sommerfeld was nominated 80 times, but he never got Nobel Prize. Lewis was nominated 41 times, but he never got Nobel Prize. And his student, he has many students got Nobel Prize. It's you know that, right? Okay, you know the feeling. If your student got Nobel Prize, and you never get Nobel Prize, what a sad story. But anyway, another great person is Pauling. He's only 4 individuals who has won multiple Nobel Prizes. He got more than 1 time Nobel Prize. In your life, if you got 1 time Nobel Prize, that's enough. Means your life finished. Normally, when we talk about Nobel Prize, once you get Nobel Prize, that means in your future you never have great achievement anymore. It's only 1 time in your life, so you never have another luck. You're not lucky enough to get another Nobel Prize. But Pauling, he got multiple Nobel Prizes. Good. Right. Okay. Let me summarize the covalent bonds here. Okay. The valence electrons in atoms is sharing, and the partial electron sharing, or we call shift, right? So, and then Lewis structure, you need to draw Lewis structure. And then you need to draw the Lewis structure like this. And you need to learn what is called shear hybridization. Shear hybridization, we give you an example as methane, right? Okay, and then topic 4 is energy of the heteronuclear bonds, or we think of the polar, right? A dipole and polar bonds. Okay, electronegativity, ionic character, and dipole and polar molecules. Okay, so I think, do we have time? So next topic is molecular orbitals and the molecular energy level diagram. So once we know the ionic bonds and covalent bonds, and especially covalent bonds, we need to know the molecular orbitals, how to form the molecular orbitals for the molecules. So we know the shapes of the atom, right? And we put 2 atoms together, we will make a shape of the molecule. Not only to know the shape of the molecule, but also we want to know the energy level diagram. Okay, so let's recall what we have learned about atomic orbitals. We can realize atomic orbitals is because of Schrödinger equation. The Schrödinger equation tells us that density the density of the electrons in the space. So this is the shapes of the atom. This is the shape of atom, and 1s, 2s, 3s. We play this in Kahoot, right? And p, the shapes of the p orbitals. And the good news is that I will say that bad news is this Schrödinger equation is very complicated. So it's not easy for you to use your to draw it easily, but you need to have a calculation to get the shapes. The good news is that Schrödinger equation is an eigenfunction. An eigenfunction is linear. Linear means that the solutions are additive. What does that mean? Solutions are additive. For example, if you have a linear equation, for example, function of x, y, z equal to k1, you got a solution of s1. And another equation is that function of x, y, z equal to k2, and solution is s2. And because this equation is linear, you can put these two equations together, and solution can be added up together. So solutions are additive. So what does it tell you? So if you have a shape of one element and you have a shape of B element, if you put these two together, these two can be added together. So this is the important thing for the eigenfunction and eigenvalue. When you learn mathematics, this is important concept, right? So the solution of the Schrödinger equation is chi. So this is what we call wave function. So wave function, the superposition of the solution holds. So this chi can be equal, molecules can be, this equation can be chi1, chi2, chi3, chi4. That means that if you have two atoms, 3 atoms, 4 atoms, 5 atoms, it doesn't matter. You can put this shape together and add this up. So that means it makes us easier to realize atomic orbitals can put it together to become molecular orbitals. So this theory is called LCAOMO. What's LCAOMO? LCAOMO is that, what is that? This is linear combination of atomic orbitals into molecular orbital. As I just told you, this is an eigenfunction. Eigenfunction can, the got answer is called eigenvalue. The eigenvalue can be put it together. The solution can be added together. So you need to follow two rules for the energy. The previous slide tells us orbital, right? The orbital, you follow LCAOMO theory. But the energy, you need to follow two rules. The first rule is conservation of energy states. The second rule is you have to follow alpha principles. There are 4 rules in the alpha principle, right? So that means that you need to follow this conservation of energy states and alpha principle. I hope you still remember when we say S, let me, do we have time? Oh no, we run out of our time today. This is very interesting and important. Once you put these two things together, let me just show you very quickly. So once you have 2 hydrogen together and you put it, you have 2 hydrogen atoms and you put this. So the shape will smear together and make another new shape for the hydrogen molecule. So hydrogen molecule, the shape of hydrogen molecule looks like this. Hydrogen atom, the shape of hydrogen atom looks like this. So these two together, you can straightforward think this is, if you put 2 things together, it looks like this. right? This is the shape. How about energy? Energy will follow two rules, right? First rule is called what? Conservation of energy state. This is called energy state. And if an energy state here, here, and then what can you do? Yet you also need to have two energy states for the molecular. One energy state, one become two. But you don't put two in here in the same level. No, you cannot. Because this is called bonding orbital. This is called anti-bonding orbital. Anyway, we don't have time to tell you the detail, but I will leave this wonderful knowledge for you to digest in next week.